Welcome back, class. In today's video, we are going to dive into the topic of solution concentration. So concentration is a way to quantitatively express how much solute is in a solution, right? So expressing the amount of solute that is dissolved in a particular solution. Now, we're of course going to focus on the quantitative ways, but you're probably familiar with some qualitative terms that are used, like dilute and concentrated, that give the idea of having a low concentration or dilute solution versus a high concentrated or concentrated solution. Now, concentration can be expressed in a myriad of terms, right? So we're going to look at several of these. They can sort of be divided into mole-based terms, like molarity, which we've already learned, molality, mole fraction, mole percent, and mass and or volume-based terms, such as mass percent or parts per million, parts per billion, etc. So we're going to dive into each of these, and then we'll do some sample problems. So, first one, molarity. I'm not going to go over this in detail. If you need to review molarity, you can look back at chapter 5 where it's first introduced. But this is probably the most commonly used unit of concentration in chemistry. You've used it already in labs in terms of having concentrations in some molal concentration, using it as a way to figure out moles in a given volume of solution, etc. So in a lot of ways, molarity is used as a way to go back and forth between moles of solute and volume of solution. And so if we remind ourselves of exactly what molarity means, right? It is the moles of solute per volume of solution. So units of moles per liter, and typically when we write something out, we express its molal concentration, or its molar concentration, as a capital M. So for example, if I say something is 2 molar, or 2.0 capital M, what that means is that 1 liter of solution would contain 2 moles of solute. In this case, 2 moles of sugar or sucrose. So now, of course, that tells me how many moles are in every liter. Now, so for example, if I had 2 liters of solution, I would automatically know that it contained 4 moles of sugar. Or if I had half a liter, I would know that it contained 1 mole of sugar. And so I can use molarity as a way to go back and forth from my volume of solution to my moles of solute. Now, one other idea about molarity that I want to express is preparing a solution. So, one of the key things is this last statement, right? When we say that it's moles per a certain volume, what that means is that is the volume of solution, not the volume of solvent. So if we're making one from scratch, and let's say we wanted to make 1 liter of this 2 molar concentration of solution that we have, what that would tell me is that I need 2 moles of sucrose for every 1 liter of solution, not 1 liter of water, right? Not 1 liter of solvent. So the first thing that I would have to do, right, would be to figure out how much mass 2 moles of sucrose is. And so the molar mass of sucrose, C12H22O11, is 342.3 grams per mole. So that means 2 moles would be 684.6 grams. So if I wanted to make up 1 liter of this solution, I would need to start with 684.6 grams of sucrose. So I would weigh this out, and then I would dissolve it in enough solvent, and this is the key, enough solvent to give me 1 liter of solution. So that may mean that I add 980 milliliters or 990, whatever it is, because that solute is going to occupy some of the volume. And so if you were just to go ahead and add 1 liter of water, right, because that's the volume of solution you need, you would end up with a total volume bigger than 1 liter, and so your concentration would be off. So the key is we weigh out the exact amount of solute that we need for our solution that we're making, and then we add enough of the solvent to get to the desired volume of solution. That's the key. Okay, so at this point, we're going to explore some of the other types of ways to express concentration. So while molarity is great, and that's the one they'll use, we should understand how to work with and what other units of concentration are. So the first one is molality. Now, yes, very similar, just off by a letter, so it's molarity versus molality. Now, molality is abbreviated by a lowercase italicized m, and it has units of, again, moles of solute, but now instead of liters of solution, it's kilograms of solvent on the bottom. Now, the one big difference here between molality and molarity is that molality is a mass-based unit, right? It doesn't have volume of solution in here, right? Now, so one of the advantages of using a mass-based system is that it is not temperature dependent. So volume-based units are going to be slightly temperature dependent because the volume can change with temperature. It can expand and contract a bit. So mass-based units won't change with temperature. So typically places where we see something like molality are going to be in temperature sensitive types of calculations, or where we're looking at changes in temperature. Okay. But a couple of key differences. Note that it's mass of solvent, not mass of solution. Okay, so that's molality. Now, the next one I'm going to look at is parts solute and parts solution. So there's several different ones of these. So it's the idea of, this fractional based, right? The part over the whole. So how much solute per how much solution. And so there are basic types of these. The most common one is a mass percentage. So is to express something as a percentage. And that would be the mass of solute over the mass of solution. So the part over the whole. Now, this can also be volume-based, right? You could have milliliters of solute over milliliters of solution, etc. So it could be mass or volume-based. Mass is much more common. And even though you will see it expressed, you really should stick to units where we have the same type of unit on both the top and the bottom of the expression. So you will occasionally see, the mass of solute per volume of solution. And sometimes medicines are described this way. But that's not really the best way to do it. You want to try to keep those units consistent. But anytime we express it as a percentage, what we have to understand is what we're really expressing is how many parts of the solute represents for every 100 parts of solution. So for example, if I have something that is 0.9% by mass, what that means is that there is 0.9 grams of solute for every 100 grams of solution. So that means that 100 grams of solution is made up of 99.9 grams of solute, 99.1 grams of solvent. And you add that up, that you get your 100 grams of solution. So it's the part over the whole. Okay? And again, this could be grams, it could be kilograms, it could be pounds, it could be any unit, but we wanted to keep matching units. So percentage based or out of 100 is the most common. But there are other related parts, types of units that we can use. And you're familiar with probably at least one of these. And these are ppm and ppb, or what we call parts per million and parts per billion. And these types of units are typically used when we have very low concentrations. So it's not really useful to express it out of 100 because there would be such a small amount for every 100 that we end up with an extremely small mass percentage. But if we make the amount of solution bigger, it's going to, of course, make the amount of solute bigger, so we can get sort of meaningful numbers if we express in these alternative units. So parts per million is probably the more common, and it's, again, the same idea, that it's the mass of solute over the mass of solution, but instead of timesing by 100, we times by 1,000,000. Parts per billion, same thing, except we multiply by 1,000,000,000. Now, oftentimes when you deal with parts per million, well, you could do it in grams per million, but oftentimes they'll divide both of these by 1,000. And so 1,000th of a gram is a milligram. And if you take 1,000,000 divided by 1,000, we get, divided by 1,000, we get 1,000 or a kilogram. So milligram per kilogram is an alternative way that we see parts per million. So if something is, say, 36 parts per million, that means there is 36, let's say, grams or milliliters in 1 million grams or 1 million milliliters, or we would say, so it could be, let's say, 36 grams per 1 million grams, or 36 milligrams per kilogram. Those would be two ways to express the same thing. Now, a couple of other things to point out, and these are sort of good general things to remember, since we're often dealing with aqueous solutions. When we have very dilute solutions, we will often assume that the density of our solution is equal to the density of water. Because for dilute solutions, there's almost no difference. And so, oftentimes in problems, we won't be given, say, a density of solution, but we know it's a relatively dilute solution in aqueous, so we can assume the density of water. And right, remember the density of water is approximately 1 gram per milliliter under sort of normal temperatures. Okay, so these are our parts based. So mass percent, parts per million, parts per billion. So now we're going to shift back to a mole based unit, and this is what we call a mole fraction. So mole fractions, first of all, are abbreviated by a script X, or this is actually the capital letter chi, but we'll just call it, the italicized uppercase X. And it's the mole fraction, and it's just what we think about a fraction might be. It's the part over the whole. So it is the moles of solute. So it's the moles of one component over the total moles. So most typically, this is going to be the moles of solute over the moles of solution. Now remember, the moles of solution is going to be solute plus solvent. So when I say moles of solute plus the moles of solvent, I could just as easily say moles of solution. But it's important to understand these nuances or what these real meanings are, because oftentimes we won't be given the moles of solution, but we will have ways to get to moles of solute, because that's the same thing here, in moles of solvent, and we need to understand that we add those together, we get the moles of solution. Now, we can also do, this is the mole fraction of solute, right? But we could also do the mole fraction of solvent, and it's going to be the same idea, but in terms of solvent. So it's going to be the moles of solvent over moles of solution. So we can express the fraction in terms of the solute or in terms of solvent. And of course, if we add those together, the fractions of all the components must equal 1. Right? There's unitless here, right? We don't have any units, it's just numbers. Now, mole percentage, which is a related unit, is just simply the mole fraction times 100, right? It's taking the mole fraction and expressing it as a percentage. So this is a way of, how we want to express it, but very much the same unit. Just we're expressing it as a percentage instead of a fraction. Okay, so this is sort of a good once-over of all of our units here. Now, when we go to do problems, we have a couple different kinds of problems, right? Sometimes we'll be given a description of a solution, and we'll be asked to calculate the concentration in molarity or molality or whatever the units might be. And so based on the information given, we can get to the different things that we need in order to calculate these different concentrations. Another type of problem would be converting from one unit of concentration to another unit of concentration. So we're going to do an example showing both of those kind of problems. So some of the things to keep in mind is, remember that concentrations can typically be written as a ratio. So while there may be a unit like molarity, molality, we have to understand what those mean, right? So if I'm given a concentration of molarity, I have to understand that I can write that as a certain number of moles per every 1 liter, right? So I can write that as a ratio. And what this does is help separate the numerator and the denominator. So it allows us to individually think about, okay, what do I need to calculate a molarity? Well, I need to know moles of solute, and I need to know liters of solution. And so I can more easily get to each of those individual parts and then combine them to get to the molarity, for example. So I can take my solute and get it in the right unit, take my solution or solvent and get it in the right unit, and use these different parts and put them together to calculate the concentration. Okay,